Hey everybody, and welcome to chapter 15. We are going to be talking about nuclear magnetic resonance spectroscopy in this chapter. Only one instrumentation in this chapter, and that's because it's so gosh darn important. NMR, nuclear magnetic resonance, is a spectroscopy. So we will be using, again, remember, radio frequencies from the electromagnetic spectrum to gain structural information about unknown organic compounds. NMR involves that interaction between the electromagnetic spectrum, which we talked about in chapter 14, and the actual nucleus of an atom. So we're focused on the nucleus, not technically any other bonds per se, but what we will focus on is different types of nuclei, specifically the ones proton, hydrogen 1, and carbon 13, right? Those carbon 13 and hydrogen 1 NMRs are what we will be diving into. We'll talk about the other different kinds of NMR that could possibly occur, but we'll focus on carbon and hydrogen nuclei for our analysis. I write there for obvious reasons. We love carbon, right? Organic chemistry, the study of carbon and all the reactivity that it can do. And it's really what's helpful about NMR is the structure, the connectivity of a molecule is going to affect how the radiation interacts with the nuclei. And so it's a very important way to decipher structural connections. IRs for functional groups, mass spec is for the mass, the molecular formula, some structural information, but not much. NMR is the end all be all of organic spectroscopies here, organic instrumentation that tells us the actual connectivity of compounds. So protons and neutrons are in the nucleus. Hopefully remember that. And they behave as if they are spinning, right? So think about them as protons, at least, are positively charged, right? And they're spinning around. Neutrons are neutrally charged. They're in there as well, spinning around. If an atom has an odd number of protons or an odd number of neutrons, it will have a net nuclear spin, right? So overall, the things in the nucleus need to be odd in number, right? And so typical ones, this is what we call proton NMR. We've called hydrogen a proton before, so hopefully that's not anything too crazy. Carbon 13 NMR, remember carbon 13 is about 1.1% of isotopic abundance of carbon in every carbon-based molecule. Nitrogen 15 is also existing, fluorine 19, and phosphorus 31. We don't deal with these ones in this class, but just so that you know, they do exist. There are other types of NMR spectroscopies that are important to the world. We will be focusing on proton NMR and carbon 13 NMR. The spinning charge of a nucleus creates what we call a magnetic moment, and that magnetic moment is a magnetic field. Think about the same idea as magnets, right? Atoms are tiny magnets, and that's amazing to think about. Just the same idea as a magnet has a north and a south pole. If you think about the magnets on your refrigerator, if you have those, my son adores those Brio trains that have magnets and have a north and a south pole. So he is all about magnets right now and seeing how they connect or that they push away and things like that. For an atom, if we think about the direction of motion here, direction of rotation, the axis of the spin and of the magnetic moment is right here in the middle. Right? There you go. And those magnetic forces are spinning around in flux around that nuclei. All right. Now, normally, those atoms have disordered magnetic moments. They are magnetic moments that are just floating around in space, right? Floating around wherever the molecule ends up being. What we are going to be doing in an NMR is providing an external magnetic field. And that external magnetic field is going to align the magnetic moments of the molecules. So think about these as all the little nuclei, right? And then all of the nuclei are going to become aligned. Notice how some of them are pointing up and some of them are pointing down. So nuclear magnetic, right? That's the first two letters that we are going to be seeing in NMR, the nuclear and the magnetic idea. They are going to be attracted to a magnetic field, specifically because there's an odd number of them. And so those magnetic moments will align with or against, right? Some are up, some are down. With the magnetic field, alpha, opposing the magnetic field or opposite of the magnetic field or against the magnetic field, beta. What does that even mean? Well, it means that when they line up, there's either the alpha spin state or the beta spin state. Now, beta spin states against the magnetic field is higher in energy. The alpha spin state is lower in energy, okay? And what I really want to hone in on here is the idea that these two different energy spin states are going to be exposed to the magnetic field, and also, here's where the spectroscopy comes in, they're going to be exposed to radio waves. It's just the right amount of energy difference between the alpha and the beta spin state to get these spin states to flip, to change. The stronger the magnetic field, the greater the gap will be. And so we'll get a better change in energy here. So the stronger the magnetic field typically aligns with something that is more sensitive of an NMR, right? So we're taking a magnet, we're going to apply that magnetic field to our compound. The nuclei will align either with or against that magnetic field and create an alpha and a beta spin state. Now that change in energy is going to be right around the change in energy of radio waves. And so we can talk about the photons being absorbed to flip and spin the alpha to the beta spin states. Now, the applied magnetic field causes the electrons to circulate, inducing an opposing magnetic field, which is called diamagnetism. The nuclei are experiencing less of the external magnetic field with these opposing electron magnetic fields, right? So depending on the environment, right, the difference between the alpha and the beta spin states could be different based off of what the nuclei, the proton here in question, we're just doing a little proton, right, for proton NMR first, what the hydrogen there, the nuclei of the hydrogen is experiencing based off of what's around it, right? So nuclei surrounded by less electron density are said to be de-shielded. Nuclei around more electron density are what we are called shielded. And their energy to flip between the alpha and the beta spin states are different. So we're really looking towards the amount of radio wave necessary to flip between the alpha and the beta energy, right? And that's what we're trying to detect. So when the alpha spins are flipped to beta spins, energy is absorbed, and that is what we call resonance, okay? We're going to call nuclear magnetic resonance when the alpha spin state, right? We're thinking about alpha and beta here. When we can flip the alpha up to the beta spin state, that is the term resonance here. It's a totally different term than when we're talking about electrons moving in resonance in a molecular orbital. I know. Why not choose a different term out of all the words? Why are we talking about resonance here differently than resonance previously? I don't know. I wasn't the old white guy that decided to use the same term. I'm real sorry. Can't change it now, maybe later. But when we're talking about the magnetic field, the applied magnetic field, we said the stronger the magnetic field, the bigger the gap will be. Now, magnetic fields can be measured in Teslas, not the car, but the magnetic field. 1.41, small NMR, there's a small energy gap. The radio energy wave required to resonate between the alpha and the beta spin states is not that great, right? The stronger the magnetic field, the greater the distance between the alpha and the beta spin states. Why this is good is we get a more sensitive NMR, we get a better reading. And so that idea of being able to see the different types of environments around each nuclei becomes a little bit easier to see. Now, how do we actually acquire a proton NMR? Written like this with H1 up there, proton NMR spectrum. We take a really, really big magnet, and that magnetic field is created when a high current passes through a superconducting material at extremely low temperatures. Typically, in this superconducting magnet, it's cooled by liquid helium around 4 Kelvin. Very expensive, very important to keep that liquid helium around the NMR. Why is it important? Well, because if the NMR gets too warm inside, then the magnetic field will actually demagnetize itself. All right. Usually we see the radio frequency excitation pulse is put in there. It's called a pulsed Fourier transform spectrophotometer. And that's the radio energy being used to excite the sample. And each of the atoms is excited and then relaxes, and it emits energy, and it's excited to the beta spin and relaxes back to the alpha spin. All right, so it's that alpha and beta resonance that we're trying to record, right? You don't need to know too much about the Fourier transform or the idea of the free induction decay that the book talks about. What I really want us to get into is the characteristics of the output, right? We have a big computer then off to the side, and we really want to make sure that we can read that. In the lab, if you get to go into the lab and see the NMR, it's really important that you understand it's a huge, huge magnet. So be really careful about your credit cards and your wallets and your cell phones. Yeah, it can demagnetize things that are also magnetic around you, right? So usually jewelry or wallets or cell phones are not allowed in the NMR, as long as it's a big one, right? Very expensive unit, very detailed to run. So typically smaller benchtop NMRs are seen in organic chemistry labs. If you go into any sort of graduate program or higher research, you might find an actual huge NMR that's like the big cylindrical thing that we saw in the picture from the textbook. A couple of characteristics with the proton NMR spectrum. We're going to focus right now on hydrogen. We'll get to carbon. We don't spend a lot of time there. We're going to spend more time on proton NMR. But the NMR spectra contains all the structural information that we need. We want to talk about the number of signals. How many things do we see here? 1, 2, 3. We want to talk about the location. Where are they on this axis, right? The intensity is going to be determined by the area under the curve. If you've taken any sort of higher mathematics where you've done area under the curve ideas, we don't need to do that here. But we will talk about how do we develop the area under the curve. It will be able to tell us the number of hydrogens present in the signal. And then again, the shape. We have a lot of splitting here. We see a lot of peaks versus maybe only 4 peaks versus maybe only 3 peaks, right? So we'll talk about all 4 of these characteristics for NMR. We'll start with the number of signals. The number of signals in a proton NMR spectrum indicates the number of different kinds of protons in a compound. Identical protons are called chemically equivalent protons. Chemically equivalent protons fall into 2 different categories, homotopic or enantiotopic. So we want to really make sure we can visualize a compound. This is where molecular model kits are really helpful. I'll talk about the molecular model kits that you've received in lab last semester. If you took organic chemistry last semester. If you don't have a molecular model kit, there are a couple of apps that are good, and also I'll give you my preferences. But visualization, I think this is one of the hardest parts with understanding proton NMR, is making sure we understand what is chemically equivalent and what is not. Homotopic protons are chemically equivalent. They're identical protons. They would show up in the same signal, and they appear if the molecule has an axis of rotational symmetry that allows one proton to be rotated onto the other one without changing the molecule. So these two on the first structure are homotopic because we have identical symmetry over here. Where is the axis of rotation? Right there. There's the axis. Rotation would be if I were to flip around, right? Flip around that axis, do a pancake flip. Same thing with the middle protons. We're looking at these two. Symmetry exists right here. And again, rotation around that axis, pancake flip, they align. If the fluorines were different in the middle compound, if the methyls were different on the compound on the left, these would not be homotopic anymore. All right, so we have symmetry here. Last one, plane of symmetry, kind of plane with the three-membered ring there. Even though we have a wedge and a dash, if we were to rotate around that plane of symmetry, the three-membered ring would still be in the same spot. And so the hydrogens on all three of these examples are equivalent to each other. Another test for homotopic protons can be the replacement test. We replace with a deuterium. Remember we talked about deuterium before? Deuterium is heavy hydrogen. It's a hydrogen with, instead of one proton in the nucleus, it's a proton and a neutron in the nucleus. So we often use it for isotopic purposes to distinguish between different compounds. We'll talk a little bit more about using deuterium in reactions when we get into reactions, but think about it as a labeling technique here. So how do you do the replacement test? If you replace one hydrogen with a deuterium, and then you are able to flip and superimpose on a second compound with the other hydrogen being a deuterium, and you can superimpose them, then they are homotopic, all right? So again, take the compound, split it up into two, deuterium on one side and deuterium on the other side, and then see, can these be superimposed, right? Are they superimposable or are they non-superimposable? That is the question. Enantiotopic protons are going to be if the molecule has a plane of reflection that makes one proton the mirror image of the other, enantiomers, right? So see how we don't have symmetry here, but the replacement test is still going to help us, right? Before, the replacement test showed us identical compounds. If we do the replacement test and we find enantiomers, then the resulting hydrogens are enantiotopic, still identical, right? But not homotopic. And so the replacement test will be helpful to identify enantiotopic or homotopic equivalent hydrogens. Still, they would show up in the same location, right? But they are a different kind of relationship. So again, split the compound up, change one hydrogen to deuterium, just as the label, change the other hydrogen to a deuterium. And then again, decide what the relationship here is between these two compounds. These are enantiomers, right? Enantiomers would then be enantiotopic protons. If the resulting compound was superimposable, like we saw previous, that's homotopic. If the resulting compounds are enantiomers, enantiotopic. Still chemically equivalent, right? Whether you have an axis or a plane of symmetry. If neither of those relationships exist, then you have a diastereotopic or non-chemically equivalent set of protons. The replacement test will also be able to prove diastereomers. Notice here on this replacement test, we take one hydrogen and the other hydrogen and replace deuterium. Deuterium. What is one big, take a moment, just take a pause. How would you identify these as diastereotopic, maybe even without doing the replacement test? What was a diastereomer? A diastereomer are two compounds where one chiral center stays the same and the other switches. We are creating a chiral center by doing the replacement test, right? This is just a theoretical type of consideration. But notice how there's already a chiral center in this molecule. When there is a chiral center in the molecule, there's no rotational axis of symmetry, there's no plane of symmetry. So hydrogens, CH2 groups, are going to be non-chemically equivalent. All right? Couple of shortcuts that you can take to identify is if you notice a CH2 group, right? The 2 protons on a CH2 group will be equivalent if there's no chiral centers in the molecule, right? With the compound here on the left, no chiral centers, those CH2s are chemically equivalent. If you see the 2 protons in a CH2 group and you see a chiral center somewhere else on the molecule, think diastereotopic. Those are going to be not chemically equivalent protons. What does that mean? These will have the same signal. These will be different signals. All right. If there are 3 protons on any methyl group, they will always be equivalent to each other. We're talking about CH3 groups, always going to be equivalent. You don't even have to do the replacement test. Nope. Last shortcut, multiple protons can be equivalent if they can be interchanged through rotation or a mirror plane, right? So these CH2 groups over here in this ketone, there is a rotation of symmetry right here. So we will see these 4 protons as chemically equivalent. Also, these 3 protons are chemically equivalent to each other, as well as the 3 protons on the other side. So this compound, we would see 2 signals. One set of signals for the inner hydrogens, the CH2 groups, and the other signal for the CH3 groups.